Now we're ready to actually apply the Nernst equation to a particular problem. So the first example that we're going to look at is, let's say that we wanted to build, if you want to build a galvanic cell that has a voltage E cell non-standard of 0.80 volts. So we want to build a galvanic cell that has a voltage of 0.8. We're going to use zinc and copper, and we want to have a zinc 2+ solution that is 2 molar. So we have a particular voltage we're looking for. We know that we want to use zinc and copper for whatever reason. Our zinc solution needs to be 2 molar. So let's figure out what concentration of copper, let's use copper 2+, what concentration of copper 2+ is needed for us to get this voltage. So our first hint when we're looking at a problem like this, and the first clue or 2 clues that we have that this is a Nernst equation problem is that, number one, we have E cell and it's not standard. It's not an E standard cell. So that's clue number 1, that this is going to be a Nernst problem. And then clue number 2, we have a molarity that's given to us and it's not 1 molar, and it's asking us to come up with a second molarity. So these are both hints that we're dealing with a problem where we need to use the Nernst equation. So I am going to start solving this problem by, that I like to rewrite the equation that I'm going to use, just so that I can think about what kind of variables and pre-calculations are necessary. What kind of things do I need to figure out before I can actually answer this question and solve this problem? So here's the Nernst equation, the version that I like to use, the natural log version. And so let's take a look at this and figure out, what do we need to plug into this equation? Well, first of all, we're going to need to figure out E cell standard, this guy right here. So we know that this is going to be the cathode minus the anode, and since this is standard, this is coming from the data table, the standard voltage of the cell. So we're going to have to look that up in the standard reduction potential table. We're also going to need to figure out what the half reactions are for this. We need to know what N is, how many electrons, and that's going to come from the half reactions as well. So we're going to need that for that. And then we also need to know Q, products over reactants raised to the stoichiometric coefficients. So for this, we just need to know the whole entire reaction that's taking place. So I think that what we're going to do here, let's start with going to those data tables and finding the appropriate half reactions. And I know that I'm looking for a zinc and zinc 2+ combination. That's going to be one of my half reactions. And I know that I'm also going to be looking for a copper 2+. That's going to be my other half reaction. So let's go find our data tables and let's see what these equations look like. And I've got this really marked up here. So let's just get rid of some of these. And we are looking for, this is our alphabetical sheet. So we're looking for copper, and we want to make sure that we're finding the right copper. Copper and copper 2+, that's the equation that the half reaction that we're using for this one. So there's that voltage and the half reaction all balanced out. So let's take that back to our notes and let's plug that in. And that one said copper 2+, plus 2 electrons makes copper. And you know, I really need to be including the states in this because the states are going to matter since we're writing a Q. Got to stop leaving those off. And the voltage for that, the standard voltage for that was 0.337, I believe. We'll double check when we go back to it. So now let's go look for the zinc half reaction. Back to our data table. Oh, I really copied that wrong. 3419. 3419. I got to fix that. Okay. I don't know what I was thinking. So now let's go find our zinc reaction. Down at the bottom of the table. Oh, it's already marked for us. Zinc 2 plus aqueous, and the voltage for that is negative 0.7618. I'm going to write that down first. Negative 0.7618 volts. And that reaction was zinc 2 plus aqueous plus 2 electrons makes zinc solid. Now, remember, in this data table, everything is being written as a reduction because that's how we tabulate it. That's standard. But only one of these half reactions is actually a reduction, and the other one is an oxidation, which we're going to have to flip it around. Now, in previous ones where we've said we're going to calculate the voltage E cell, and when we're calculating E cell, we know that it's cathode minus anode, but we also know, since we're dealing with a galvanic cell, that the voltage is just positive. So we don't really need to think that much about what order we are plugging these half reactions into this equation. Only one answer or only one order is going to give us a positive answer, and whatever that is, it's going to be correct. So our two options here are 0.34 minus negative 0.76 or negative 0.7618 minus 0.3419. And we can see that that second option is not correct because it gives us a negative voltage, which is not possible. No negative E cell when we're dealing with a galvanic cell. It has to be a positive voltage. So that means that the first one that we have up here is the correct order for our voltages. 0.3419 plus 0.7618 gives us 1.1037 volts. So we've got that part figured out, and that's this part of the Nernst equation. So I'm going to try to do some color coding here. So we've got this figured out, and it's right here. So let's move on to the next thing. The next part that we're going to tackle is the moles of electrons N. And we're going to, like I said, we're going to get that from the half reactions and the overall equation. And in our half reactions, we have 2 electrons in each of the half reactions. So that is perfect for our particular reaction. N is going to be 2. And that, again, is coming from those half reactions. So that was easy. The last thing that we need to figure out here is the Q. This one's going to be a little bit trickier. So we've got the Q, and we know Q is products over reactants raised to the stoichiometric coefficients. What we don't know is what are the products and what are the reactants in this. In order to figure out products versus reactants, we have to figure out the right order to write these two half reactions, the correct order to write our half reactions. We know that one of them needs to be turned around, but we don't know which one it is. We can figure it out. It's very important for us to do this correctly because Q depends on us knowing which is the product and which is the reactant and putting them into that fraction in the correct order. So our tool for coming up with the correct reaction is our E cell, because we know that E cell has to be positive. We put everything together in an order that gave us positive 1.1 volts. We also know that E cell is the cathode minus the anode. So we found that the correct order of voltage in our E cell equation was the 0.3419 minus negative 0.7618. This was the correct order to give us a positive voltage. And because this is the correct order, we know that the copper 2 plus, is our cathode, and the zinc 2 plus, is our anode. Now, if you're feeling kind of like, whoa, I just took a huge leap there, we know that this order is the correct order to give us a positive voltage in E cell. We know that E cell is cathode minus anode, and so from that, we are saying that the cathode has to be 0.349, which is copper. So that's how I'm coming up with this. And the anode has to be the 0.76, negative 0.76, negative 0.76 is with the zinc reaction. So that's where these assumptions are coming from. So we've got a little bit of it figured out now. We know that the copper is the cathode, and we know that the zinc is the anode, and we know that our cat is red, which means that the cathode is where the reduction takes place, and the anode is where the oxidation takes place. And we know oil rig, which means that the reduction reaction is adding electrons to the reactants, and oxidation is loss. So here we are losing electrons as products. So all of these are going to help us put our two half reactions in the correct order. Our cathode with the copper needs to be written in the order that shows electrons being added, and that's how it already is. Electrons are being added to our reactants, so that's perfect. Our other half reaction, the zinc, needs to be written in a way that shows electrons being lost, coming out as products. So the zinc half reaction is the one that we have to turn around. Now we can combine the two together to get the overall Cu2 plus zinc solid makes Cu solid plus zinc 2 plus. And those two electrons are canceling out, so I'm not going to bring them down. And this is our overall equation written in the correct order, which we are going to use to come up with Q. Products over reactants raised to their stoichiometric coefficients, leaving out solids and leaving out liquids. So there is our expression for Q. Whole lot of work being done to set up this E-cell Nernst equation thing, but we're there. We're finally ready to plug stuff in. So let's do that. I'm going to rewrite down here because it's way up at the top of the page. E-cell non-standard is equal to standard E-cell minus 0.0257 over N times the natural log of Q. And now I'm going to plug in all of the stuff that we figured out. We figured out our E-cell. Let's go find it. E-cell was 1.1037 volts. 1.1037 volts. And then we are going to subtract 0.0257 over N. We figured out our N, the number of electrons. There, it's right there. Number of electrons is 2. Times the natural log of Q. Our Q is over here. And one of these concentrations we know. Let's go back up to the problem and see which one it is. And the problem tells us zinc 2 plus concentration is 2 molar. So we'll just put that right into the equation. 2 molar over the copper 2 plus concentration, which is what we don't know. The problem also tells us the E-cell non-standard, our desired voltage, 0.8. So we can plug that in as well. So So we are ready to solve this problem. This is going to be an amazing mathematical experience to solve this problem. What we're trying to solve for is this copper concentration down in the bottom of a fraction that we're taking the natural log of. Oh my goodness, how exciting. So I'm going to try to do this. I'm going to try to hold my horses and do this slowly for you. If you're feeling uncertain about your ability to do the math, but I'm just so excited to do this math. I might skip some steps. I'm going to try really hard to not. So first thing that I've done there is just moved the 1.1 over to the left side. And this, I've rewritten it. And so now I'm just going to get rid of the negative sign since they're on both sides. So now what I'm going to do is multiply both sides by this fraction so I can get rid of it. I'm trying to isolate this whole part of the equation as much as I can. So I'm going to get 0.3037 volts times 2 over 0.0257. I think there's, I feel like this is a volt. I'm missing a unit on there. A volt there. So that those volts will cancel. And that's going to be on the left, on the right-hand side, we're going to be left with the natural log of 2 over the copper ion concentration. Our volts cancel, and times 2 divided by, not times 3, times 2 divided by 0.0257, I am getting 23.63 is equal to the natural log of 2. I'm just going to say x in place of that copper concentration. We're going to unnatural log both sides. Oh, that's a big number. E to the 23.63 is equal to 2.0 over x. E to the 23.63 times x is equal to 2.0. X, which is our copper concentration, is crazy small. 1.09 times 10 to the minus 10 molar. So think about that. How would you go about making that solution? How do you make a solution with a concentration that is 10 to the minus 10? Probably not going to be very accurate. If this was what you were actually trying to do in the real world, if I was doing this myself personally, and in order to get the cell to work correctly, I had to have a molarity that was 10 to the minus 10, I would go back to the drawing board of my voltaic cell and I would say, you know what? I need to make some changes here. I either need to change my desired voltage, or I need to change the ingredients that I'm using in this reaction, or I need to change my initial voltage of zinc, because that is going to be really difficult to pull off.